Okay, so in this recording and lecture, we're going to finally get to some substantial material. And by that I mean we're going to begin our study of logic. Now, this course is, as I mentioned in the previous lecture and the one before that, this course is going to be different than your typical math class. We're going to learn how to argue why things are true or false in a formal manner. We're going to learn how to apply these techniques to proofwriting, to algorithm design, and we're really going to nail down what it means to argue and act in a formal manner with regards to mathematics. Now, in order to do that, we need to spend a few weeks on logic. Logic is the fundamental tool used by mathematicians and by computer scientists to prove that statements are correct or to prove that algorithms return the correct value or that algorithms are a valid solution to a given problem. So we begin with what's called propositional logic. Now, there's going to be quite a few definitions going forward in the next few weeks. I apologize, but that's just what we have to do. And each time we enter into a lecture with logic, we're probably going to have to start with a definition like the following one. And this is the fundamental definition of the following few sections. So a proposition is a declarative statement that is either true, typically denoted by capital T, or false, typically denoted by capital F. Okay, so just like in math courses like pre-cal or calculus or algebra, you kind of have like a realm that you're in, and the realm is either real numbers, natural numbers, functions, and then once you have this fundamental item, you start building on that item. In logic, the fundamental item is a proposition. We're going to learn how to manipulate and work with different combinations of propositions. So we should probably look at some examples first, honestly, before we start doing any of that, in order to really make sure that we understand what this definition means. So let's see. What is an example? So maybe something like maybe like Rice University is a private university. So this declares a statement, and we can check whether or not it's true or false. Okay, so this satisfies the definition of being a proposition, and its truth value is true. Rice is a private university, so that's another term that we need to remember. So the truth value of this proposition is true. Okay, so that's another term that I'll be using quite a bit. Now, What would be another example? Something like possibly, say, 2 plus 3 is equal to 4. That is a declarative statement, right? It says that this is equal to that, which we're interpreting it as how we understand the equal sign, and it's going to be a true or false statement. In this case, it's false. So the truth value of this proposition is false. Okay. So something that would not be a proposition would be something that is dependent on the observer reading the statement, right? Like saying that, I don't know, like Romy is a cat, for example. That's a declarative statement. Romy is a cat, right? But it's vague, it's not precise. Like my cat's name is Romy, but I got the name Romy from the movie Romy and Michelle's High School Reunion. So it's also a character. So it is different values. So the name Romy is always a cat would be false because I'm being very specific, but it's kind of vague in how you're gonna have to interpret that, right? Like, so what would be the precise way to make it not a proposition? Let's just say, or you could make it like a question to really mess it up, saying, is Romy a name only, or something like you can play around with it in that by doing so, you kind of it becomes difficult to kind of realize the right way to go, or not the right way to go, the right way to interpret these values. But in the simplest case, it's just a very clear thing that is always either true or false. Oh, so like, is the sun yellow? That's a good one. Is the sun yellow? For some people, it'll be white. For some people, it'll be orange. It depends. That would not be a proposition. In this case, we would avoid that. So that's not going to be what we deal with. All right, so just getting that out of the way. So next up, I'd like you to observe that we're writing these declarative statements, and it takes a lot of time, right? It's kind of cumbersome even to write the statement over and over again once we know that it is a proposition and we want to kind of work with it, right? And this is where we want to introduce propositional variables. So this is a part of notation. So we will typically note propositions by lowercase letters. Such as P, Q, R, S, ... So invoking this notation will make it easier to talk about a proposition without having to write it all over again, right? So in this case, I might say that the proposition Rice University is a private university. I'll call this the proposition P. And the proposition 2 plus 3 is equal to 4. I'll call this the proposition Q. So then, now that I've assigned these to variables, I can say something like P is true and Q is false. And if I forget what the propositions are, I just go back to where I defined them. Okay. So, pretty straightforward so far, I hope. Next up, we have to talk about operating on these propositions. So we can assign them to variables, true or false values, truth values. Next up is operating on them. Which leads us to another definition. So the negation a proposition P okay, denoted by that little symbol there, P. It reads not P, is the proposition it is not the case that P. So this is the negation of a proposition P. Okay. Now this takes in a proposition and then returns a new proposition. So we can think of this as an operator on propositions. It's the first one that we've learned about. So if we're looking at this proposition P right here, Rice University is a private university, the negation of P would be what? So if that's my P, then not P is, it is not the case that Rice University is a private university. It's kind of a long-winded way of saying that Rice University is not a private university. So yes, the formal definition is to say that it's not the case that P, but you can interpret this in an easier manner if you wish. So one way, as I just wrote down, it is not the case that Rice University is a private university. Another way would be simply saying Rice University is not a private university. Okay? It depends on how you want to interpret it. Okay. Now, what is the truth value of this statement? Not P. This statement here, so not P has truth value false. Now this is important to think about. The original statement P had a truth value that was true. The negation of P has a truth value that's false. This is true for all propositions. There is a binary relationship or dichotomy between the truth value of the original statement and its negation. And we can represent this relationship with what's called the truth table. So the way that a truth table works is it's a grid of truth values, either true or false, right? And the column names are the propositions that you have in question. So for example, here I have P, and for this column name, I'll have not P, okay? Now, along those columns, as you go down, we're going to enumerate the possible choices of true and false. So for P, since it's just a single blown proposition, it's either going to be true or false. Now, if P is true, the negation of P is always going to be false. If P is false, the negation of P will be true. So along the rows of the truth table, you see the relationships on the labels of the columns in the truth table. Okay? It's a way of quickly describing the relationships with a diagram or a table. Kind of reminds me, as a Python programmer, of a pandas data frame. But they're very simple, and it's just enumerating the possible truth values for the different combinations of a proposition and other stuff. Okay. So if we understand this truth table, I can use another truth table to introduce the other operations that we can perform on propositions. So suppose we have a proposition P and a proposition Q. So we're looking at two propositions now. Just like if we were looking at two different numbers, we can add them, subtract them, multiply them, all these things. With propositions, there's going to be similar operations that we can do. So propositions only have two different values, right? True or false. So in these two columns here, we're going to enumerate all the possible combinations of the values of P and Q together. So P can be true, Q can be true, P can be true, Q can be false, P can be false, Q can be true, and then finally they both can be false. So those are all the possible combinations of truth values between P and Q. Now, in these other columns, I'm going to introduce notation that will represent several definitions that we need to learn about. The first one will look like this. And then in this column, I'm going to write down the value of whatever this is. I'm not telling you what it is yet, but whatever this is, the value of this operation with respect to these possible truth values. So in this entry here, true. In this entry here, false. This entry here, false. And this entry here, false. So, does anyone want to take a guess at how they would define that operation based off of these values? If P and Q have that, then that. If P is that and Q is that, then that operation is that. So forth and so on. How would you describe this in words? I'm looking at my chat right now. I keep on seeing and. I'm assuming that you've watched one of my previous lectures or you've been reading the textbook. But just in words, how would you describe it? This is true only when what? This operation is true only when what? Both P and Q are true, right? This operation has a value true only when both of those are true. And it's false every other place, right? So P and Q is the conjunction. That's the name of it. The conjunction of P and Q. And is only true when P is true and Q is true. Okay. So that's the name of that operator. It's the conjunction operator. It's read as P and Q. Yeah.
I have a question. So is this pretty similar to Logic 1? Because I took that at UHM and this looks kind of similar.
It's about the same, yes.
About the same.
The notation might be different, but it's about the same.
Okay, cool.
So this is read P and Q is only true when they're both true. Okay. Next one. So there's the next operation. How would you define that? Not the name of it. How would you define it? Just like I wrote a definition in words for the conjunction, how would you write that other one in words? And I'm waiting in the chat to see if anyone writes out anything. So I saw where either P or Q is true. Yeah, that seems to work. I would maybe word it a little bit different and say something like this. So first off, I'll give you the name of it. This is the disjunction. P and Q. And is true whenever at least one P and Q are true. Okay, and this reads P or Q. Okay. So that's the disjunction. And it's true whenever at least one of P or Q is true, and false otherwise. Okay. Next up, I have this one. So what do you think? How would you define that with words, that operation? Anybody? I see some of you are chatting me the name of it, but how would you define it with words if you're trying to describe what this is doing to someone else? So I see true when they are different and false when they are the same. I like that. That's not the way that I would define it, but I do like that. The formal definition that I've always used is that this operation is true only when exactly one of them is true and false otherwise. So this is called the exclusive OR operation. And is true only when exactly one of P and Q are true. Okay, so that's the exclusive OR operation. All right, so I'm running out of room. I guess I'll continue it right here. So I'm just going to enumerate all the possible values in these two columns. And introduce another operation. Okay, so that's the next one. So how would you define that operation in words? Any guesses? Waiting, waiting. When is this operation true? When is it false? Trying to describe it to someone else. P arrow Q. All right, so I'll go ahead and let you know. So P arrow Q is the conditional operation. It reads, if P, then Q, or Q implies P. And is true, so if P, then Q, maybe I'll say is only false when P is true and Q is false. That seems an appropriate way to define it, right? If we look at the rows of our truth table, we see that the only place where it is false is when P is true and Q is false. Okay. Now, this one is really important. They're all really important, but this one is especially important when considering mathematical statements. So a little bit about the notation here. P arrow Q, in that case there, P is called the hypothesis. And Q is called the conclusion. So more terminology, it's really important. Okay, So the conditional statement, if P then Q, is only false when the hypothesis is true and the conclusion is false. That's the only time that that happens. Okay. Now we have one more. P double arrow Q. With those entries there for its truth values, depending on the combination of truth values of P and Q. How would you define that? P double arrow Q.
It's only true when both P and Q are the same.
There you go. That's it. That's exactly the definition. Maybe I might reword it a little bit, but that's more or less it. Almost forgot to highlight this word. But yeah, so P double arrow Q, it's called the biconditional. Statement. And is only true when P and Q have the same truth values. Okay, so this is the biconditional statement. This reads if and only if. So that's how you would read that. All right. So all of these operations are, we've exhausted the list of all the basic propositional operations between two propositions. When you have two propositions that are connected via one of these operations, you have what's called a compound proposition. It's a new proposition that's made up of other propositions. So if we recall P and Q from earlier in lecture, we can see how they work. We can apply these operations to those two example propositions. So I'm going to shorthand P and say that it was the proposition Rice is a private university. And Q was the proposition 2 plus 3 is equal to 5. So those were our two example propositions. So looking at the conjunction operator, does it make sense that these would be the truth values of the conjunction operation? Well, we have to read it out loud. The conjunction of P and Q is read P and Q. So the conjunction of that P and that Q would read out what? Rice is a Rice is a private university, and 2 plus 3 is equal to 5. Is that true? No, it's false. Think about that again. Rice is a private university, and 2 plus 3. Oh, sorry. Why didn't y'all say anything? 4. I was thinking 4, but I wrote 5. Didn't help myself. All right, try it again. Rice is a private university, and 2 plus 3 is equal to 4. That's a false statement because at least one of them is false. And that's what this operation is conveying, this conjunction. So next up, let's look at the disjunction. So the disjunction is read P or Q, right? So looking at these propositions, Rice is a private university, or 2 + 3 is equal to 4. At least one of those is true, which means that that or is going to be true on those propositions. Next up, exclusive or. That one's a little bit harder to read out and has more applications when writing programs. Let's just try it. Rice is a private university, exclusive or 2 + 3 is equal to 4. That one's kind of harder. It's not as clear when like wording it out or like saying it out loud. So let's move on to the conditional, which is probably the one that's going to annoy you the most. So P arrow Q is read if P then Q, right? So let's use that P and that Q. So if Rice is a private university, then 2 + 3 is equal to 4. That's false, according to the definition, right? Because P is true and Q is false. But if we reverse it and look at if Q then P, what's the truth value of that proposition? Let me make this a little bit bigger. So if Q then P, what is this truth value of this compound proposition? Well, let's read it out. If 2 + 3 is equal to 4, then Rice is a private university. That's also true, according to the definition, right? This is also true. What about something like 2 + 3 is equal to 4? So if that proposition, then 1 equals 0. What's the truth value of this conditional statement? So if 2 + 3 is equal to 4, then 1 is equal to 0. It's true. I like that in the chat, all of you are saying true. Now, in the past, I've had students kind of groan about this definition because for whatever reason, their first instinct is that this should be false because that's false and that's false. But why would we define it to be true? Like those are definitions that we made up as humans, right? So why did we decide that this would be appropriately labeled true? And I think the best way to illustrate why this should be true is done by relating it to programming. So imagine you're writing a program and you have a conditional statement somewhere in your program. You have an if statement and then stuff is happening after that if statement, if the if statement is satisfied, right? Well, you could have all kinds of bugs following the if statement. All sorts of bugs that if your program tried to run that, your program would crash and fail. However, if the if statement, like this if statement being false means that your computer program will never enter in and ever look past it. So even if the following, even if the conclusion of your conditional statement is mess and it's false and would cause bugs or whatever, if the if statement, the hypothesis is never satisfied, you never go in to check the truth value of what follows it. So this is a really important point from both programming and from writing proofs, is that when considering the conditional statement, whenever the hypothesis of the statement is false, you don't check. You never go into the block of code or the block of arguments to evaluate what's happening on the other side. It doesn't matter if it's true or false, it's still going to run, it's good to go. The only time when you have a conditional statement that you do have to be wary is when the hypothesis is true. Then, if the hypothesis is true, you go in and you have to check the conclusion. And if the conclusion is false, the whole statement's false. If the conclusion is true, the whole statement is true. Very important point. Maybe just like write it in your notes. For conditional statements, if the hypothesis is false, the statement's always true. In fact, it has a name. It's called vacuously true. Okay? But if the hypothesis is true, then you have to go and check the conclusion. Okay? So, really important point. All right. Next, I want to kind of call your attention to the biconditional, the if and only if statement. Notice in the definition that the biconditional is only true when the truth values are the same. So what this is really hinting at is that if we would like to somehow define logical equivalences between propositions, logical equivalences, we might have to make use of this operation. Because if we have propositions that are always the same truth value, whether both false or both true, that might be a way of us defining how to like encapsulate or capture these notions of like truthy equivalences. So we will get to actually defining logical equivalences in next lecture. So I think I'm going to go ahead and pause the recording.